Hello, we are Team TQ'd undergraduates from the University of Moratuwa, Sri Lanka. We are presenting our approach to solve the ICASSP Cup 2021 task. The goal is to maximize the received data rate for each user. There are two types of users: line-of-sight users that directly receive signals from the IRS and non-line-of-sight users that receive the signal after reflecting off other surfaces. All the channels that do not include the IRS form the uncontrollable channel. Our task is twofold: extracting information from the dataset and estimating both controllable and uncontrollable channels faithfully. Secondly, to search the optimum IRS configuration for each line-of-sight and non-line-of-sight user. For each user, the same set of pilot configurations are set in the IRS. Then the received signals are recorded. Afterwards, in the local device of each user, the algorithm runs. We have simulated in a Raspberry Pi 4 device. The channel is estimated and then an optimum configuration is found in 1.3 seconds. The user then informs the IRS with his desired configuration. Considering data rate, the fast implementation achieves 99% of the maximum data rate we achieved. Therefore, the proposed solution achieves a high data rate in a small time, even when using a general-purpose resource-limited processor. So how did we achieve this result? This is the high-level view of our solution. For the first subproblem, which is channel estimation, we use the pilot configurations in the datasets. Then we use a linear model to characterize the system and use multivariate multiple regression to estimate the channel. The estimated channel defines a mapping F from any IRS configuration to the received data rate. For the second subproblem, which is configuration search, we use the mapping F to search the IRS configuration space. Two algorithms, a genetic algorithm and a gradient descent algorithm, are used sequentially to optimize an IRS configuration for each user. For channel estimation and configuration search, we identified some key challenges. For estimating the channel, the first challenge is that most details about the channel properties, such as physical model of the IRS and the surrounding, are unknown. Secondly, we must decide whether to separately estimate the channel for line-of-sight and non-line-of-sight users. Once the channel is estimated, we have a mapping from a configuration to a data rate. For configuration search, the combinations of all possibilities is effectively infinite. So the challenge is that the IRS configuration is in discrete space. Therefore, defining optimization objectives, loss functions, and gradients is not straightforward. Furthermore, if we somehow map the IRS states to a continuous space, the complexity of the mapping F results in a non-convex optimization problem. Finally, all these should be addressed in a real-world application of wireless communication. Thereby, the entire computation should cost minimum time and hardware resources. Solving the first challenge involves inferring from data. Dataset 1 had abundant data for one user. Analyzing this dataset led to the noise variance and other channel properties. Modeling the channel as an FIR filter gives a linear relationship y equals xb plus e, where b is our estimation target. The maximum likelihood estimate for the channel is therefore the least squares estimate. It includes the controllable channel B and the uncontrollable channel HD. We observe that each tap in B is periodic. This justifies the geometry of the IRS to be square-shaped. HD resembles a typical multipath fading channel, and its faithful representation is significant, especially for non-line-of-sight users. Thus, both B and HD should be estimated accurately. We concluded that dimensionality should be reduced as we will have more unknowns than data points. Now that we have inferences, we proceed to estimate the channel. Since our task is set for OFDM transmission, one channel tap can be modeled as a narrowband channel. The spatial model for each tap is based on existing work on spatial channel sparsity. Relating this to our linear model, we conclude that each column of V characterizes one such channel tap. The spatial model suggests that when the altitude angle theta approaches 0, a column of V becomes periodic. Our inferences showed the necessity to reduce dimensionality. Therefore, we use these properties to reduce the dimensionality of P from having 4097 variables per tap to 65 variables per tap. Now we modify the rest of the terms accordingly, and we have a reduced dimensionality. Furthermore, we have a channel estimation method, which is common for line of sight and non-line of sight users. Even though the obtained least squares estimate is simple, it led to better results. We can now estimate the channel easily for both non-line of sight and line of sight users using the same linear model. Next challenge is the discrete nature of the search space.
Disregarding physical defects of IRS elements, each element is in a binary state. It is modeled by +1 or -1. To facilitate a gradient-based search, we relax the discrete space into a continuous space from -1 to +1. Further, we mapped this bounded continuous search space to an unbounded search space that is the entire real number line. This allowed us to easily use the data rate function R to define a cost function for the gradient descent. After running gradient descent in X domain, we can find a configuration, but the computational cost in terms of hardware and time is high, and the objective function is non-convex. After mapping to a continuous space, we must now deal with non-convexity. Heuristics provide gradient-free, fast yet suboptimal configurations. The binary nature of each IRS element fits well with genetic algorithm. This takes less resources than the gradient method. We inferred that vertical strip patterns give higher data rates. Therefore, instead of naive implementation of mutating each element, we can enforce a periodicity to the final configuration. This resulted in reaching 99% of our overall highest data rate in the competition in 1.3 seconds on a Raspberry Pi 4, as we showed in our simulation before. This chart is a summary of our configuration search approach. Only using genetic algorithms is the fast mode and was used in our initial simulation. If we want to improve our accuracy by sacrificing some resources and time, we can use the genetic algorithm's output as a warm start to the gradient descent algorithm. Therefore, we are combining the speed of the heuristic with the precision of the gradient descent. This is the precision mode. If we further want to improve the data rate by spending more time and computational resources, we can run gradient descent and genetic algorithm alternatively. Then, if we are in a local minima, we can possibly escape from it through a mutation in the genetic algorithm. With this, we have a complete algorithm to estimate the channel and search the configuration for each user. The summary of our performance shows that the fast mode is roughly 800 times faster than the precision mode, and also it achieves 99% of the highest accuracy obtained by us in precision mode. In conclusion, our solution uses carefully selected, simple algorithms to achieve an effective solution. It can be used to achieve high data rates in fast mode, and it can achieve slightly higher data rates in precision mode. It is practically feasible, with the entire process completing with minimum time and hardware. And for both line of sight and non-line of sight users, the same pipeline can be used. Thank you.